Well, thanks everybody for coming this morning. Sorry for the delay. GoToMeeting is never straightforward and always filled with interesting complications. Luckily, this was an easy fix. I'm really happy to be here today to introduce Charles Schutte to you guys. Everybody knows him in the room. His parents are in the back. They're very proud, I'm sure, because he's going to be defending his dissertation today. Charles joined us about 6 years ago. I remember his visit to UGA vividly because Sophie Claire was a month old and we had a dinner party at my house, and that was interesting. But she did really well and Charles did really well, and he decided to come here despite the fact that I had a screaming child and was sleep deprived and probably couldn't speak very legibly. But since he's been here, he's done some really outstanding work on Cabrera Island primarily, but also in association with the LTR project, looking at groundwater dynamics in coastal, in this case, a beach face, but also coastal hammocks and marshes. And I have to say that he's been one of the most productive students I've ever had in the lab, and he's been an exceptional role model for the other people in the group. So for me, it's been a pleasure to have him. I'm going to hate to see him leave. He's going to be joining Dirk de Beer's group at the MPI in Bremen in November. But for the next 45 minutes or so, the floor is all his, and he gets to tell you about what he's been doing for the last 6 years.
All right. I'm going to start my timer over here. I'll try to keep it under 2 hours. So thanks for being here. I'm really excited to tell you about the work that I've been doing on nitrogen cycling and greenhouse gas dynamics in shallow aquifers. I want to start off by saying thank you to, there, we'll do that so my formatting comes out right. By saying thank you to a lot of people. I couldn't have done this without, I need to speak up. I wonder if I just need to come stand next to the computer here, which is okay. So I couldn't have done this work without a lot of help from a lot of different people. Of course, I wanted to thank my advisor, Mandy, and my entire committee, which is Christoph Miley, Marianne Moran, Alicia Wilson, Billy Moore, and Bess Ward. There have been a lot of people in the Joy Lab over the course of the last 6 years who've helped me out a lot, but I want to point out 3 people in particular who have made substantial contributions to my work. Kim Hunter, Vladimir Samarkin, and Marshall Bowles. And then in the Wilson lab, Tyler Evans and Joey Anderson. Couldn't have done this without them. And there are a number of people who have come and I did a lot of work on Sapelo Island. I spent months down there, maybe close to a year or 2 total of the time that I've been here. And I've had a number of people who came and bailed me out of really tight places when I was trying to get experiments started and didn't have enough hands. And those are Daniel Saucedo, John Ledoux, Rick Peterson, and Patrick Hutchins. I also want to thank my family, my wife Virginia, who can't be here because she's doing field work in Panama, and my parents, Brian and Deb, who are in the back. Hi, Mom and Dad. And here they are, coming down on vacation to come help me on Sapelo Island. I also had a lot of friends who helped with a number of things through the course of the last few years, but this is a short list of people who came down to help me out with field work, either physically with an auger or emotionally keeping me sane while I was there for months at a time. And of course we had funding from primarily the EPA and NSF I need to send out a special thanks to, but also the Georgia Coastal Ecosystems LTR project, the University of Georgia Graduate School, and then of course I couldn't have done any of this work without all the support from the Marine Institute on Sapelo Island. So I want to give you a quick orientation to the rest of the talk. I'll start with an introduction, of course, and then I'll be talking about nitrogen cycling. I'll move on to greenhouse gas cycling, and then I'll close with a few conclusions. So let's kick off the introduction. This is a cross-section of Barrier Island, the type of Barrier Island where I work. And it's kind of a nice representation of a lot of different types of coastal environment that we find on the coast of Georgia. There's an upland in the center of the island that has trees growing on it. If you go out towards the beach, there's a sandy dune system and a beach and then the ocean. On the other side of the island, there's a salt marsh and then a tidal creek. And there are a few different kind of key features that I want to point out to you about this type of island. The first is that there's groundwater within the island, and then there are tides in the ocean, the tidal creek. So we have a high tide line, a mid tide, and a low tide line represented out here on the ocean side. These islands have complex stratigraphy. This is probably a somewhat simplified view where there's mud layer on the salt marsh back here that extends beneath the island here that's buried by overwash of sand from the beach when there's storms and things like that. So there's a sand layer that sits on top of everything, and there's a mud layer underneath that, and another sand layer that's even deeper. And there's a lot of islands that probably have even more layers than that, but we're going to keep it relatively simple here. There's a freshwater lens that forms in the center of the island. What was that?
Don't know.
Okay. As it when it rains on the island, oh, let's skid away. I wonder if they're actually here to listen.
I just hang up on it.
Okay, hang up. Hope no one was actually hoping to listen. Right, I was talking about the freshwater lens. When it rains on the island, the fresh water percolates down through the sediment, and then it floats on top of the relatively dense seawater that underlies that lens that makes its way into the aquifer from the ocean. There's groundwater flow. You can see the water table is elevated under the center of the island. It acts a little bit like a water tower. It drives flow away from the center of the island towards the ocean on one side and the tidal creek on the other side. And then, of course, there's not like a really distinct boundary between fresh and salt water. As the groundwater is flowing out towards the ocean, it mixes with the saline groundwater. And then finally, that groundwater discharges into the ocean and the tidal creek. And the one other key feature that I want to point out here, this is a static photograph of what the island looks like at any given time. But that's subject to change. So here is a picture of 2 of our wells on the beach in October of 2009. And there's 2 things I want to point out that I have highlighted here. One is there's this joint in this well where in the PVC of that well, you can actually keep track of to see how the beach is changing. And these two wells that are back here, back behind the dunes right now. If we move forward through time, January 2010, you can see that joint is a little bit higher above the sand than it used to be. In August of 2010, it's a little bit higher yet. March of 2011, this well's starting to look really tall. We haven't lengthened it. The beach is starting to go away, and those wells that used to be behind the dune back there are now on the beach itself. In October of 2011, we actually had to cut that well off so we could still reach it. Before that, we'd been standing on stacks of coolers on the bed of a truck to get to sample it. We finally just took a hacksaw to it. And then in July 2012, these wells are very firmly on the beach. So everything I'm going to be talking about today is against the backdrop of a really rapidly changing barrier island system. They're not static. And I'm going to be coming back to this sort of schematic cross-section representation of the barrier island throughout the talk. I'll be adding arrows and things to it. So when you see that again, that's what that is. So why do we care about this type of system? I would argue that one good reason is that a lot of people live there. Half the world's population lives within 200 kilometers of the coast, and that number is growing all the time. 8 of the 10 largest cities in the world are coastal cities. And in the US in particular, we've invested a lot of money in infrastructure and housing. We've been building homes on the beach or near the coast anyway at a rate of 2,000 per day and for the last 40 years. That's a lot of money and resources. And speaking of resources, this is, the reason that so many people are concentrated on the coast. There's a lot of things that are unique to the coast that go on there. The oceans provide a unique and efficient way to transport goods around the world that drive a lot of the global economy and generate a lot of wealth. And we need a place to load and unload those goods on the coast. Tourism is a huge driver of the economy in the United States and around the world. And our beaches in the US have a really disproportionate impact on tourism dollars that are spent here. Fisheries, also a huge generator of wealth and also of protein that people need to eat. And then finally, it provides everyone who works in these industries and a place to live nearby. There are 2 key threats to these resources, that our ability to use these resources, that I'm going to highlight in this talk. One is eutrophication. The primary production in coastal systems tends to be limited by the availability of nitrogen. So we're adding a lot of nitrogen, humans are, to these systems. And when that happens, algae bloom. When they die, they sink. They're consumed by heterotrophic organisms, and that uses up oxygen in the water column. And this is a problem for our ability to use coastal resources. We like to come down here to fish for tourism. When we add a lot of nitrogen, we can get fish kills, get these algal blooms. It makes it a lot less fun to hang out on the beach. And groundwater is important to this nitrogen loading to coastal systems. We tend to think of rivers as being the dominant input of nitrogen to the system. But studies have shown that around the world, groundwater discharge can rival the riverine input of nitrogen to the marine environment. And it's particularly true on the coast of Georgia. So here we have a representation on the schematic of the cross-section of the island. The groundwater tends to be enriched in nitrogen relative to surface water, and that groundwater is discharging and carrying nitrogen with it. And the other threat I want to highlight is climate change. Climate change is driven by 3 dominant greenhouse gases in the atmosphere. It's carbon dioxide, methane, and nitrous oxide. In this chart, you can see the concentrations of these gases in the atmosphere have been relatively static over the last 11,000 years. It's actually 800,000 years. And they've gone up rapidly in the last 100 years in response to human activity. This has resulted in an increase of about 1 degree Celsius in the average temperature of the planet in the last 100 years, which in turn has heated up the ocean, causing it to expand. It's melted glaciers and ice caps and has led to about 19 centimeters of sea level rise over that time period. And sea levels continuing to rise at a rate of 3 millimeters per year, which doesn't sound like a lot until you're in a house sitting behind a levee or a dune system and there's a storm coming, and you only, the difference of a few centimeters can make the difference between flooded and not flooded. So this can have a huge impact on our economy. And again, I'm going to make the argument that coastal groundwater has an important role to play in this issue of climate change. If we were to take a little bit of sediment from Barrier Island, you can see we have our sand grains blown up here. And there are microorganisms that live in that sediment that are producing these gases, carbon dioxide, nitrous oxide, and methane. And other people have gone out and measured the actual flux of these gases from salt marsh sediments to the atmosphere, from estuaries and tidal creeks and the coastal ocean. So we know that these gases are being exported to the atmosphere from coastal systems. And I'm going to try to address the role that groundwater has to play in that export. So a quick orientation to the study site that I'll spend most of the time on today. This is Cabrera Island. It's a little thin barrier island on the coast of Georgia near the Marine Institute. It's about 200 meters across, which is really convenient when you're carrying a car battery to sample your wells. And the other thing to point out about this island is that it's relatively pristine. There's very little human impact here. So we're kind of getting a look at, to the extent that we can, how this kind of island works without a lot of extra human activity. So this is a little bit different view of our cross-section of Barrier Island, of Cabrera Island. The dark black line here is the sediment surface on the island. You can see we're 200, 250 meters across here on the x-axis. Each of these circles represents one of the groundwater monitoring wells that we installed in the summer of 2008 and then sampled every 2 months for about 2 years afterwards. You can see they range from about 1 meter deep down to about 5 meters deep beneath the sediment surface. And this top chart here shows the concentration, the median concentration of nitrate in those wells over that 2-year period. And the bottom chart shows the median concentration of ammonium. So these are 2 different forms of dissolved inorganic nitrogen. The blue colors are low concentrations and the red colors are high concentrations. And so what immediately jumps out is there's this one well up on the upper part of the beach in shallow groundwater where there's a whole lot of nitrate and really next to no ammonium, which is the opposite pattern that we see in all of these other wells where there's plenty of ammonium and really no nitrate at all. So this tells us that there's something interesting happening with the nitrogen cycle in the groundwater here. So here's a representation of the nitrogen cycle. There's all kinds of different forms of nitrogen on this chart. The y-axis here shows you the oxidation state of those different forms of nitrogen. Up at the top of the chart is the most oxidized form of nitrate, and down at the bottom we have our most reduced forms of ammonium. And most of the dissolved inorganic nitrogen in groundwater is going to be trapped in the form of ammonium. Aquifers tend to be very reduced systems with plenty of organic matter and no oxygen. So the nitrogen is going to be trapped down here as ammonium. But what we saw on that one well on the beach is that there's a lot of nitrate there. So what that suggests, the nitrate isn't coming from the ocean or somewhere else in the aquifer. It has to be being produced at that location. And there's one microbial process that can do that. It's called nitrification. And it requires oxygen for its activity. And I'm pretty into the nitrogen cycle, so I think that's cool by itself. But if we're interested in groundwater as a source of nitrogen to the ocean, this is also interesting because nitrate is a substrate for other microorganisms that reduce nitrate ultimately to dinitrogen gas, which is what makes up most of our atmosphere and is not available to organisms to take up and use in their biomass. So it's not bioavailable. And my hypothesis for this portion of the work that I'm presenting here was that a coupling between these processes is taking place within these coastal aquifers that's removing bioavailable nitrogen from groundwater before it can be discharged into the ocean. So to investigate that, I wanted to know how much oxygen is actually present in the aquifer, because we know that nitrification requires oxygen. So I installed these mini piezometers in the shallow aquifer in the upper part of the beach, right at the very top of the water table, basically. And you can think of this as just kind of sticking a soda straw down and slurping on it. So I connected this gas-tight tubing to a pump that was sitting up behind the dune where it was sheltered, and pulled groundwater out of the aquifer at a very low flow rate, and pumped it past this YSI sonde that was collecting dissolved oxygen data every 15 minutes for months at a time. Hooked up to a car battery, it had to be switched out twice a day. That was fun. Right. So what I ended up with was this a data set that looked like this. This is over the course of most of August in 2012. The blue line shows the dissolved oxygen concentration. So you can see that sometimes there's not much oxygen, but then sometimes we get these big spikes of dissolved oxygen. And the black line is the tidal signal from a nearby surface water body. And originally I thought that this oxygen signal was driven by the tides. And if you've seen me give a talk anytime in the last 2 years, you've probably seen me talk about how that was the case. And I thought that because there's this nice correlation between these dissolved oxygen peaks and high tides on spring tides. But then I looked into the data a little bit more closely and realized that there are other times when that oxygen peak doesn't line up with the high tides nearly so well at all. So I went back and looked at the data a little more carefully and added the green line here as photosynthetically available radiation. And what you can see is that doesn't matter what phase of the tide we're on. Spring tide is over here on the left. This is a neap tide over here on the right. High tide, low tide, it doesn't matter. These oxygen peaks always coincide with the availability of light for primary production. So this oxygen that's being driven deep into the aquifer is probably the result of photosynthesis that's taking place in shallower layers of the sand on the beach. And I wanted to know what the response of the nitrogen cycling community was to these oscillations in dissolved oxygen that we saw from basically 0 up to almost atmospheric saturation. So I took sand from this location, and in some cases I didn't add any nitrogen to it. For some bottles I added nitrate, and some bottles I added ammonium. Some of them I started off under anoxic conditions and some of them under oxic conditions, and then half of those I left under those conditions for the entire time, and the other half I switched either from anoxic to oxic or oxic to anoxic. So we could see what the response is to these shifts in dissolved oxygen concentration. And the treatment that I want to point out is over here when I added ammonium and started off under oxic conditions. This is perfect conditions for nitrification to be taking place. And sure enough, we saw a production of nitrate there, indicating that the nitrifying community was active. When I switched those bottles to anoxic conditions after a few days, nitrate was consumed, indicating that one of the processes that consumes nitrogen under anoxic conditions could be denitrification or anomox, or dissimilatory nitrate reduction to ammonium was active. So that's suggesting that that coupling that I talked about before was taking place and nitrogen was being removed. I'd like to know how quickly that's happening to see what impact that might have on coastal ecosystems. So we have a rate over here that I measured with these bottles. The problem with that is that when you take sand from the aquifer and put it in this bottle, you're removing groundwater flow from the equation. And people have shown in the past that when you do that, you get a lower rate of, a lower reaction rate than you would if you were to actually measure the rate that's taking place in the aquifer itself where groundwater is flowing. So I wanted to try to get an idea of what this rate is that's actually taking place in the field. And to do that, I use this observation that we have this spot where there's a lot of nitrate. At that same location, this shows the nitrous oxide concentration in all of these wells. It's a very similar pattern. There's no nitrous oxide anywhere except for this one spot where there's a lot of nitrate. So nitrous oxide production seems to be associated with this place on the island. And I want to try to use nitrous oxide as a proxy for this nitrate removal process that we think is taking place. So there are 3 processes that can produce nitrous oxide: denitrification, dissimilatory nitrate reduction to ammonium, and nitrification. And based on evidence from these incubation experiments, I think that denitrification is the dominant process that's generating this nitrous oxide. For one thing, the nitrous oxide was only produced under anoxic conditions, so the nitrifiers wouldn't have been active. And the other thing is that I also measured the production of ammonium. So under anoxic conditions, this nitrate could be being reduced to ammonium, but I measured that and subtracted it out of the nitrate reduction rate, so that all that was left should have been from this denitrification reaction. I know some of you are thinking to yourselves right now, but nitrous oxide is a greenhouse gas, and you're still on the nitrogen part of your presentation. I'm using nitrous oxide as a proxy for these other nitrogen cycling processes right now. We'll get to the greenhouse gas part in a little bit, I promise. So to measure the concentrations of nitrous oxide in the field, I use this photoacoustic field gas monitor. It's a really cool instrument. It actually allowed me to make measurements in real time, so I didn't have to drive 5 hours down, collect a sample, drive 5 hours back, spend a long time in front of a GC. I could actually see what was happening in real time on the beach. But in order to do that, you can't just inject groundwater into this instrument. You'll ruin it. So I had to connect it. I had to build this device to connect the field gas monitor to. And that's an equilibration chamber. Looks like this. Show and tell time. Who wants to start with it? You can pass it around. Here you go, Ryan. So as you can see, it's just a PVC pipe. It's about 40 centimeters long. And there's a watertight silicone rubber membrane around that. So this prevents the water from getting into the chamber. It's filled with gas, and that allows the nitrous oxide to equilibrate across the membrane, so I can actually measure the nitrous oxide content within the aquifer. I stacked 4 of those equilibration chambers inside a PVC housing, and then buried that down to 2 meters deep within the aquifer. So starting from the sediment surface down to 2 meters deep, taking measurements of nitrous oxide at half-meter intervals. And the reason I did that, those of you who are looking at this and can see there's a tear in that membrane, right? So we need to do something to protect the membrane, put in this PVC armor. And that nitrous oxide depth profile looks like this, measured in the winter here and the summer here with the open circles. And you can see that in this depth interval from 0.5 to 1 meters, there's a lot of nitrous oxide. And I have a little representation of what sand profile looks like on this part of the beach over here. So we're looking like sideways through this depth profile right now. If you were to flip this thing up and look down on it, I'm assuming this is 1 square meter. So we're looking at this 1 square meter depth profile of sand in the, on the upper beach here. And based on this data, it looks like there's nitrous oxide production taking place in that 0.5 to 1 meter interval. It's at the very top of the water table. So I wanted to see, I measured the rate of nitrous oxide production there, but it's the same deal inside a static bottle. So I wanted to get another way to look at what that production rate is. And what I did is I built a mass balance for nitrous oxide within this sand column. So we think that nitrous oxide is being produced here within this box. So we wanted to look at what the export pathways are for nitrous oxide from that box. And one is advection. Excuse me. Since there's high concentrations of nitrous oxide here, and we know that groundwater is flowing through that box out towards the beach, it's carrying that nitrous oxide with it. The other is dispersion. That's what these vertical arrows are, and I'm going to explain briefly what I mean by dispersion. If we take a little bit of the sand and blow it up big and look at it, we know there's groundwater flowing out towards the beach through that sand. If we were to inject a little bit of a concentrated tracer at one end of this little box, and then watch how it moves through time, it can't just be transported laterally through here, right? Because it's going to run into the sand grain. So instead, different molecules end up going different directions around all these sand grains, and you end up with a tracer that gets spread out and less concentrated. And you can see that that's that tracer is moving in the vertical direction. So that's why I have these vertical arrows here for dispersion. Both of these processes, advection and dispersion, are dependent on the groundwater flow rate. And Tyler Evans built this really cool model of the hydrology of the beach. We can see the colors of these arrows represent the rate of groundwater flow at this location. And right up here is where this sand column takes place in the upper part of the beach. And you can see that that's right at kind of a break in the groundwater flow patterns here. So a little bit farther down the beach from here, the groundwater is moving faster at about 55 centimeters per day. A little bit uphill, the groundwater is moving a little slower at more like 5 centimeters per day. And that break in the groundwater flow is dependent on the high tide line. So on spring high tides, when the high tides are high, they're going to be up above here a little bit, and this point on the beach is going to be, the groundwater is going to be flowing at that faster rate. On a neap high tide, when the high tide's a little lower, down here somewhere, we're going to be in that slower flow regime. So we average that out over the course of multiple tidal cycles and assume that the kind of average groundwater flow rate is around 30 centimeters per day. And that's what I used in all the calculations to come. So based on that, we have an advection rate of about 12 micromoles of nitrous oxide per day out of that box. And the dispersion rate is much harder to constrain. So it could be really low, it could be really high. I needed a better way to come up with what that rate of dispersion actually is. So to do that, I looked at the loss pathways from this top surface layer of sediment here, because the only input of nitrous oxide to that zone is dispersion. So I measured the flux of nitrous oxide out of the top of the sand and into the atmosphere. That was about 8.6 micromoles per day. And I also measured the rate of nitrous oxide consumption in that sand. That was about 6.5 micromoles per day. So adding those together, it's about 15 micromoles per day, and that had to be balanced by this dispersive flux. So I'm going to bring that dispersion rate of 15 micromoles per day back to this production zone here. And this production has to balance all of these loss arrows here. So the production is 2 times the rate of dispersion plus the rate of advection, or about 42 micromoles per square meter per day. That's all cool, but I started off by saying that I wanted to use this rate of nitrous oxide production as a proxy for the other nitrogen cycling processes that are going on in the system. So I'm going back to the sand incubations, and I measured that this nitrous oxide production about a little less than 1% of the nitrate that was reduced or consumed in these bottles ended up as nitrous oxide. The rest would have been as dinitrogen gas, presumably. So what I did is I divided this rate of nitrous oxide production by that ratio to end up with a nitrate consumption rate of 11 millimoles per square meter per day. So that's why that unit changed there. That's probably just a number to a lot of you. To me, that's a really high rate of nitrate reduction. That's higher than what you find in most coastal sediments. So this is a really, this is a pretty cool location. So we have these groundwater-derived nitrogen fluxes to the coastal ocean. And I talked about these daily oscillations that we see in dissolved oxygen concentration and how they're coupling processes within the nitrogen cycle and potentially removing bioavailable nitrogen as it's on its way out towards discharge to the ocean. All right, so moving on to the greenhouse gases part of the presentation. I still have some time, good. This is the same cross-section of Cabrera Island that I've been showing you, but now we have methane concentrations over here in the different colors. And you can see that there's a lot of methane kind of hanging out underneath the middle of the island here and not a lot on either side of it. And that is largely controlled by the hydrology of the island. So methanogenesis is the microbial process that produces methane, and it's going to be favored in fresh water. So this place where we see a lot of methane and presumably methane production in the Barrier Island aquifer is right where the water is fresh. And I wanted to look at what happens to that methane as it moves out from the center of the island up here out towards the ocean. And these colored boxes each represent one equilibration chamber. So this is one that I installed in the middle of the island where we saw the very high methane concentrations, obviously. And I have a transect out down the beach to the low tide line, near the low tide line on the beach. So the red colors are high methane concentrations, the blue colors are low methane concentrations. And I want to point out that there are actually 3 aquifers beneath this beach. The first is this unconfined sand aquifer that sits above the mud layer. This mud layer itself is its own aquifer. It basically acts as a wall for groundwater flow. The groundwater can flow through it, but much, much slower than it flows through the sand layer above it. And then finally, there's a confined sand layer beneath that mud layer that's separated from the sand above it by the slow groundwater flow through the mud. So I have measurements of the concentration of methane from each of these aquifers. These are kind of averages across all the measurements that I made. In this unconfined sandy aquifer, the methane concentration is quite low compared to the other measurements that I made, 0.11 micromolar. That's actually still very high relative to atmospheric equilibration. Concentrations are higher in this mud layer, more like 22 micromolar, and in the confined sand layer, they're very high, over 700 micromolar. This is looking at the same model of the hydrology of the island that I showed you before. And the average rate of groundwater flow through the unconfined sand layer is about 65 centimeters per day. And we're looking at a length scale of about 100 meters from where the methane is produced at the center of the island to where it's going to discharge at the low tide line. And that results in a residence time of groundwater in that aquifer of about 160 days. I'm ignoring the residence time in the mud layer because, as you can see, all of the arrows are down through the mud layer. The groundwater in this aquifer doesn't actually discharge to the ocean. In the confined sand layer, the groundwater flow rate there is much slower, 2.5 centimeters per day, the same length scale, but you end up with a residence time of more than a decade. Now, methanotrophy is the microbial process that consumes methane. And I measured it in 2 of these aquifers. In the unconfined sand layer, we had a high rate of methanotrophy, about 10 millimoles per square meter per day. In the mud layer, there wasn't a measurable rate of either methanotrophy or methanogenesis, so we have a rate of 0 roughly there. And this confined sand layer was just a little deep for me to hand auger into, so I don't have a good measurement there. But based on what we know about the concentrations of methane in these 3 separate aquifers and the residence time, we can make some inferences about what the rate must be in these locations. So if we're interested in the rate of discharge of methane from these aquifers, it can't be coming from this shallow, unconfined aquifer. This rate of methanotrophy is too high for methane discharge to be happening there. It's all being consumed. But I measured methane concentrations in surface seawater, and most of the time they were around equilibration with the atmosphere. But a few times we got these pulses of methane, like right in the surf zone on the beach, and that was probably coming from this confined sandy aquifer down here where the methane concentrations are high. But that requires the rate of methanotrophy to be really, really low because the residence time is so high within that aquifer. Just covered that, sorry. All right, so I've been talking about what's happening kind of on the front end of this island from the center of the island out towards the beach so far, and we're going to switch and look at the other side of the island now where the salt marsh is growing. So here's a little representation of a salt marsh. And salt marshes are cool places because they're trapping carbon and storing it in the soil. So tidal creeks tend to have lots of particulate material, these little brown dots here, and there's organic carbon that's associated with that particulate material. And when the tide comes in and inundates the marsh grasses slow the water down and allow those particles to settle out, and that traps the organic carbon in the sediment of the island, of the salt marsh. The other way that these grasses sequester carbon is through photosynthesis. So they're taking carbon dioxide from the atmosphere, fixing it into organic carbon, and then storing that in the soil of the marsh. And this is called blue carbon. It's kind of a hot topic right now. A lot of people studying it because salt marshes are storing carbon at a much higher rate than than forests on land. So even though they occupy a relatively small area, they could still be important globally. And this has implications for climate change. Obviously, if we're taking carbon dioxide out of the atmosphere and storing it in sediment, then we're slowing down the rate of the accumulation of that gas in the atmosphere and potentially of climate change. The problem is that, as I talked about before, the microbial community within the sediment is producing methane and nitrous oxide, as well as some carbon dioxide. And these 2 gases are much more potent greenhouse gases than carbon dioxide. So if you're sequestering carbon dioxide but producing a little bit of these other gases, the net effect on the climate could even out. And people have measured that flux of these gases from the salt marsh soil to the atmosphere. And we still think that salt marshes are having a net positive effect on the climate. But we've only looked at this one pathway for greenhouse gas emission, the flux from the soil to the atmosphere. And for the most part, ignoring this flux, potential flux from groundwater discharge. So I'm going to be talking about that arrow for the next couple of minutes. Here's Cabrera Island. I've been talking about that a lot so far. I've added 3 more sites with salt marshes that are all located at different places around Sapelo Island on the coast of Georgia. Each of these orange lines shows where there is a transect of groundwater monitoring wells, much like the one that I showed you for Cabrera Island. And these are about 2-year data sets for all 4 of these sites where I collected samples to measure the activity of radium, of different isotopes of radium in the groundwater wells, as well as the tidal creeks that are adjacent to these marsh sites, as well as the concentrations of these greenhouse gases within the aquifer and within the tidal creek. So I wanted to estimate the rate of groundwater discharge from the salt marsh into the adjacent tidal creek. And to do that, we used radium as a tracer. So this chart shows 2 different radium isotopes, so 228 radium on the y-axis and 226 radium on the x-axis. The squares are radium activities in groundwater wells. The triangles are radium activity in the tidal creek, and then the circle down here is the radium activity in the nearshore ocean water. So what you can see is that there's a lot more radium in the groundwater than there is in these other water bodies. So that's one thing that makes it a good tracer. And the other thing is this nice flat line indicates that the activity of radium in the tidal creek is driven by mixing between the activity of radium in the groundwater and in the ocean water nearby. So we can use that relationship to try to estimate the flux of groundwater by building a mass balance of the radium. So radium can be, in this tidal creek, can be coming from several different places, from a freshwater river nearby, it can be coming from the ocean, or it can be coming from groundwater discharge. As we just saw, the groundwater is much more concentrated than the tidal creek water, which is much more concentrated than either of these 2 sources. So that excess radium that we see in the tidal creek has to be coming from the groundwater. And then the radium, we're assuming that the only loss process for the radium in the tidal creek is by mixing with the ocean nearby. So if we're going to mass balance the radium, then the inputs of radium from groundwater have to be equal to the loss of radium by mixing. So we did some calculations to estimate this loss by mixing. And that had to be equal to the amount of radium coming from the groundwater, and we know the activity of the radium in the groundwater, and we can use that information to calculate the volume of groundwater that has to be discharging into the creek. And then knowing that volume of groundwater and the concentration of these greenhouse gases that's in the groundwater, I could estimate the flux of those greenhouse gases from the marsh sediment, from the marsh groundwater into the creek. And that looks like this. So these gray boxes are the flux of inorganic carbon, methane, and nitrous oxide from the groundwater into the creek. And I've added several values from the literature to these boxes as well. And the white boxes show the equivalent flux of these gases directly from the marsh sediment to the atmosphere. So we're comparing those 2 greenhouse gas loss pathways. And what you can see is that the flux of greenhouse gases from groundwater discharge is on the same order of magnitude as the flux from the soil surface to the atmosphere. So this is a very important process for carbon sequestration in salt marshes that's been ignored up until now for the most part. So we conclude that the flux of greenhouse gases from salt marsh aquifers to the adjacent surface water bodies is as important as the flux of those gases from the marsh soil to the atmosphere. And also that in these sandy superficial aquifers, microbial consumption of methane is a very important process that's reducing the flux of methane from the aquifer to the coastal ocean. And what this means is that methane is really not a very good tracer for groundwater, which is something that people have done in the past, use methane as a tracer for groundwater discharge. The idea being that if you see methane in a surface water body, that indicates that there's groundwater discharge happening nearby. And that's all well and good, but you're also implying that if you don't see methane in a surface water body, that there's no groundwater discharge. And I think this evidence indicates very strongly that that's not the case. And then finally, I wanted to take a step back and kind of look at this whole dissertation and try to come up with like one overarching theme, take-home message for you. And I think that is that there are these different chemicals that we find highly concentrated in groundwater on the coast, methane, nitrous oxide, nitrate, that are being produced within the aquifer. And those are driven out to discharge into the ocean or the tidal creek by groundwater flow. But there are these microbial consumption reactions that take place along this groundwater flow path that are removing some of those constituents from the groundwater before they can discharge. And these removal pathways are often ignored, but really shouldn't be. And with that, I would like to thank you for your attention. Only nice questions. Yeah.
So, self-admitted into the nitrogen cycle. How representative is this of general coastal barrier islands? I mean, you nailed Cabrera, but man, there's nothing on Cabrera. So, what I'm asking is, with eutrophication and nitrogen fertilization, things like that are going on on a very much larger scale in the coastal zones. Where is that? Is that a lot more nitrous oxide going to be put into the hemisphere, or a lot less, or what's the net impact of
Charles,
I can repeat the question. Yeah. Sorry. Okay. So I'll try to boil that down to a few sentences here. You can let me know if I got it right. The question was, so we've looked at these processes that are taking place on Cabrera Island, but Cabrera Island is very small. So how does this scale up? What does this mean for coastal environments in general?
And impacted versus pristine.
Oh, right.
Very pristine place.
Right. And so the pristine environment on Cabrera Island versus highly eutrophied, heavily human-impacted environment somewhere else on the coast. This is one of my favorite ideas for a follow-up study, actually. We know these processes are happening in an unimpacted system, and so it's kind of priming the system for consumption of nitrogen and greenhouse gases. I think it'd be really interesting to go see then, if we go to a place where humans are actively putting these compounds into the groundwater, does that mean that the microbial community there is kind of ready to go and ready to start consuming those things right away? The complicating factor would be if we're changing the hydrology. A lot of the stuff is dependent on the hydrology. So if you put in a seawall or a parking lot or something like that, I think that would probably, like for example, limit the penetration of oxygen that the nitrifying community relies on to convert ammonium into nitrate, which would in turn limit the ability of the nitrate reducers to remove that nitrogen from the system. It'd be complicated. It's a little more widespread than just Cabrera, though. I did do a survey on all up and down Cabrera and on Sapelo as well. So what I was talking about is a hot spot. It's actually a ribbon of sand along the entire barrier island, and I know that it's happening in at least 2 of our barrier islands on Georgia. It'd also be fun to see, go north, go south, and see if I can find another sandy barrier island aquifers. I think I would.
I'll ask another one.
Okay.
Temperature. If you went north, you just said go north and south.
Mm-hmm.
You said you go to New England with this. How temperature dependent? I mean, you got the rule of thumb, doubling for every 10 degrees.
Yeah.
And stuff like that. But you think that it could keep up, or you just get nothing? You just drop to nothing?
I think that you would eventually. So, excuse me. I did this seasonally. I looked for these processes in the summer and the winter, and a lot of what I showed you was from the summer, actually. When I went and looked for that nitrous oxide, in particular, in the winter, it was still a little bit elevated in that production zone, but not nearly what we saw in the summertime. And the cutoff seemed to be, I actually caught the transition from winter to summer when I was down there in March at one point. And over the course of, it was really not much more than a week. The nitrous oxide concentrations went from that low winter level up to a high summer level. And that cutoff looked like it was around 16.5 degrees Celsius. Could have been a purely temperature thing. It could have also been some kind of seasonal thing that I wasn't measuring the right things to capture. But assuming that that is a real temperature cutoff, then yeah, eventually you get far enough north that you would be shortening and shortening the window where these processes are taking place until eventually you weren't getting it anymore. Yeah, Dusty.
How sensitive is the system to drought, and how do you think drought will change your results?
That's a great question. So we've actually, I'm sorry. The question was, how would drought affect the results from this work that I've done? After spending, well, I guess I haven't been to Cabrera for a couple of years now, but I spent 4 years down there, and that happened to catch some drought periods, and it happened to catch some rainier summers as well. And the salinity gradient on the beach changes dramatically from a drought summer to a rainy summer. So that the hot spot in the upper part of the beach where there's a lot of nitrate and a lot of nitrous oxide, for some of those first summers that I was down there, we had quite a bit of rain. The salinity at that location was quite low, less than 10 parts per thousand, near zero some of the time. The last summer I was down there, we didn't get very much rain at all. It was practically seawater. And we happened to see, and that nitrate and nitrous oxide was still there. So that side of things didn't look like it was too heavily impacted by the changes in salinity. If you had enough of a drought that you were actually slowing down the rate of groundwater flow through the aquifer, then I think that would have a really substantial impact. And then, of course, the methanogenesis at the center of the island is dependent on the freshwater lens there. So if you have, that's going to shrink as you have a drought and expand as you have more rain. So I'd expect that process to integrate it over the island to kind of change in lockstep with the amount of fresh water available. Yeah.
I might have missed this. What makes the hotspot hot?
So what makes the hotspot hot was the question. I'm calling it a hotspot because the concentrations of these materials are so high relative to elsewhere in the groundwater. Is that what the question is, or are you asking why the concentrations are higher? Okay.
That was at one point. It's really interesting that you say you saw it elsewhere.
Yeah.
Yeah. Why?
That's an excellent question that I wish I had like a really good solid answer to, and really I just have ideas about why that might be the case. The fact that it always occurs at the same relative position on the beach, up like a little bit above the high tide line, maybe around the spring high tide line, near the dunes on the beach. It got to the point where I could just kind of look at the beach and go stick a probe down pretty much right into it, because it's always kind of in that same relative location on the beach. I assume that means that it has something to do with the topography and hydrology of the island. I think that the fact that there's so much nitrogen in that one spot suggests that there's probably some nitrogen fixation that's taking place there. And so I think that the thing that's different about this spot on the beach as opposed to other spots on the beach is that it's drier because it doesn't get inundated on every tide. If you go farther down the beach, the water table is going to be right up close to the surface of the beach, whereas out here, higher up on the beach, there's dry sand above it. I don't know if that has to do with that's a more favorable location for that to be taking place, or the dry sand allows faster transport of oxygen through the unsaturated pore space. I'd have to do some, I think, follow-up experiments to actually figure out a really good answer to that question. Yeah.
So Charles, you've got some nice rates there of measurements that are going on. Do you have a feeling for the spatial and temporal variability in those numbers? And I ask because a lot of your data actually has really large error bars on it in certain
You're talking
locations.
about nitrogen fixation.
Wait a second, Billy. Somebody else is asking a question right now. I'll get you next. Is that okay?
All right.
Sorry, Jake, you repeat.
So you got some nice rates,
Uh-huh.
and so, but they're averages over a wide range of data. But a lot of your data shows considerable variability.
Mhm.
Not only considerable variability, but the error bars are skewed heavily to one side rather than not symmetric. So do you have a feeling for what kind of how that variability would translate into the variability in the rates that you're estimating?
Well, I mean, the error bars on the rates are, oh, I'm sorry, I need to repeat the question. So Adrian was asking, the error bars on the concentration measurements that I showed were quite large, and so how does that translate to the error bars on the rate measurements? Is that right? And if I had shown you a plot of a similar plot of the rate measurements that I made through a depth profile, for example, the error bars are quite large on those estimates as well. I think, though, in spite of that high variability, that I'm within the right order of magnitude to make that kind of this sort of mass balance calculations that I did.
Right, so one of the things that was interesting was that a lot of the error bars are heavily asymmetric. And so is that just one point that's skewing them up to one side, or how long does those high values last versus the low values?
I got you.
That could actually skew your rates over a period of time.
Right. So the distributions on the concentration measurements were, they were not normal distributions, right? They were skewed towards the low end. So there were a few high concentrations that were kind of driving things that direction. That's one of the reasons they use medians for everything instead of averages, to try to capture that more middle measurement. And that's what I use in all the mass balance and everything as well, to try to prevent some of that being pulled out to the side by those few high measurements.
Billy?
Yeah. Back to the question of the nitrogen fixation. Why are organisms fixing so much nitrogen in this specific spot?
Right. So why would organisms be fixing so much nitrogen in this one location? Best answer I have is that this is if you look at the nitrogen and phosphorus ratios, this is probably a nitrogen limited system. Of course, I can't say that with any certainty because I didn't actually, add nitrogen, add phosphorus to see what would change the rate of production there. Aside from that, I don't know exactly what's unique about that particular location that would make it more favorable for nitrogen fixers versus some other point on the island that's also nitrogen limited.
What about an alternate hypothesis that this is a physical process by which you're sequestering very fine particulate material that then is releasing its nitrogen at that spot?
So like seawater infiltrating through the sand?
Like the beach at that spot is acting as a filter.
Right. And that's been shown in a lot of permeable coastal sediments in the past, and I'm sure that's happening to some degree here as well. The only reason, Billy, that I suspect that may not be as important here is just that that particular location high on the beach isn't inundated by the tide very frequently. So it's not to say that it's not trapping particulate material, but I would expect that trapping flux of nitrogen would be more important farther down the beach.
Yeah, it's certainly possible, but I still wonder if you have a zone like that you can trace down the beach. It's remarkable to me that would be a site of nitrogen fixation. I mean, why aren't they fixing it at other places?
Right. I don't have a good answer for that question.
Okay.
Sorry. Yeah.
This is kind of a follow-up to Brian's question, but you showed the the way that the beach eroded backwards
Mm-hmm.
over the course of your study. So did you see that, if you think that the hot spot might possibly be related to topography, did you see it move over the course of your study?
Absolutely. That was one of the things that made this. Okay, I'm sorry. So the question was, I showed that the barrier island was moving through the course of the study period. Does that mean that these chemical features that I was talking about were moving as well? And my answer was that yes, they absolutely were moving. It made it really difficult to do these kind of seasonal studies because I would go and install this equipment in the summer and come back 6 months later and it would wash away, or it would no longer, I wouldn't measure these high concentrations of nitrate or nitrous oxide anymore. So I ended up having to go down, install everything on the beach, find the spot, first of all, install everything on the beach, let it kind of sit there and equilibrate for a week or two, and then start making measurements. And then when I was done, pull everything back out, store it somewhere safe, come back 6 months later, find the spot again, reinstall everything, and do that over and over again. So the nice thing was that the feature was persistent. The thing that was kind of a drag was that it wouldn't sit still.
Can I ask one more
Yeah.
question about the car correlation that you saw in the video again? I can't remember exactly what that was correlating to.
Oh, okay. So the question,
Yeah,
I'm sorry.
And you said something about the fact that it supplied oxygen for, and I was just curious about the depth of
Oh, right.
synthetic oxygen supply to the zone of.
Right. So the question was, I showed a correlation with photosynthetically available radiation earlier in the talk, and what was that correlation to, and how does that relate to oxygen supply to the sediment? That was a correlation. What I showed was that the photosynthetically available radiation was strongly correlated with the concentration of dissolved oxygen at about 50 or 60 centimeters depth, right at the very top of the groundwater table. So I think that the fact that there's photosynthesis happening in that shallower sand is what's allowing that oxygen penetration to that greater depth.
So what's the depth difference? I mean, and how far does light penetrate in the tank?
Right, so the light's only penetrating, millimeters tops.
Well, it goes pretty deep. It actually goes fairly deep because it
Okay,
it's
right.
crystalline
I keep
sand,
hearing
so
about this and not
deeper
able.
than that. But I'm just curious as the depth separation, how you get oxygen down where you need it.
Right.
Photosynthetic
Right.
activity. It is shallow.
Right, so the photosynthetic activity is going to be relatively shallow in the sand. We see the oxygen actually showing up pretty deep, more like 60 centimeters deep. The intervening sand is unsaturated for the most part, and the circulation of gas through that pore space can be pretty rapid.
Did you ever see anything green in the sand?
Yeah, actually, I wish I had a good picture. I really only saw it on like really cloudy, like a rainstorm would come through, and then you'd go back out on the beach, and there'd be these kind of, it would look like rusty patches almost on the beach that would be there for a little bit and then disappear. So I think there are some critters living in there that are, migrating vertically, perhaps. But I need a biologist to come help me with that.
There's some in here.
Yeah.
Any other questions? Well, if not, let's thank Charles one more time.
Thank y'all.